When we ask what the most massive structure in the universe is, we first have to understand what massive actually means. Mass is not the same as size. A cloud can be enormous, yet almost weightless. A neutron star can be tiny yet heavier than entire star systems. In the universe, size is visual. Mass is gravitational. Mass is what bends space. Mass is what pulls galaxies together. Mass is what determines the architecture of reality. When astronomers talk about the most massive structure, they are not asking which object looks the biggest in the sky. They are asking which structure contains the greatest amount of matter, visible and invisible combined. And that distinction changes everything. Because most of the universe's mass is not visible. Stars, planets, gas clouds, all the glowing things we can see, make up only about 5% of the total cosmic energy budget. Around 27% is dark matter. The remaining majority is dark energy. If you try to measure the mass of a galaxy by counting stars, you are missing most of it. The Milky Way contains roughly 100 to 400 billion stars. That sounds immense. But when astronomers measure how fast those stars orbit the galactic center, they find something strange. They are moving too fast. Fast enough that visible matter alone cannot hold them in orbit. There must be more mass, unseen mass, extending far beyond the luminous disk. That unseen component forms a dark matter halo surrounding the galaxy. And that halo contains far more mass than the stars themselves. So when we ask about the most massive structure in the universe, we must include dark matter. We must include the invisible scaffolding that holds galaxies together. This immediately pushes us beyond simple visual impressions. A bright galaxy might look dominant in a telescope image, but most of its mass is hidden. Now scale that idea upward. Galaxies do not float alone in empty space. They are bound into clusters. Clusters contain hundreds or thousands of galaxies, and just like individual galaxies, clusters are dominated by dark matter. In fact, in galaxy clusters, visible matter accounts for only a fraction of the total mass. The rest is dark matter, detectable only through gravitational lensing and galaxy motion. Gravitational lensing is one of the clearest demonstrations of mass on cosmic scales. When light from distant galaxies passes near a massive object, the light bends. Space itself curves around mass. By measuring how background light is distorted, astronomers can calculate how much mass must be present. Often, the lensing effect reveals far more mass than visible matter accounts for, which means the largest structures in the universe are mostly invisible. Mass, not brightness, defines dominance. The universe is not structured primarily by stars. It is structured by gravity. Gravity gathers matter into nodes. It stretches matter into filaments. It shapes the cosmic web. And when we begin searching for the most massive structure, we are not just looking for the biggest visible object. We are searching for the largest gravitationally organized system, the region where the most matter, visible and dark, is bound or structured together. This search takes us beyond galaxies, beyond clusters, beyond even superclusters. It takes us to structures so large that their size approaches a significant fraction of the observable universe itself. But to understand those scales, we must climb step by step, from stars to galaxies, to clusters, to the vast architecture of the cosmic web. Because the most massive structure in the universe is not something you can point to in the night sky. It is something you have to zoom out to see, and once you do, scale itself begins to lose meaning. Before we can talk about the most massive structure in the universe, we need to shrink the scale all the way down to a single star. Because even the largest star is small in the grand architecture of the cosmos. Take the Sun. It contains about 99.8% of the mass in our entire solar system. Every planet, asteroid, comet, and dust particle combined makes up less than a fraction of what the Sun holds. Its mass is about 2 × 10 to the power of 30 kilograms. That number is so large it stops feeling meaningful. 2 followed by 30 zeros. A sphere of plasma 1.4 million kilometers wide, fusing hydrogen into helium, radiating energy in every direction. And yet, in cosmic terms, the Sun is average. There are stars far larger and far more massive. Some contain tens or even hundreds of times the Sun's mass. Their cores burn hotter, their lifespans are shorter, their deaths are more violent. But even those giants are still individual points of gravity. A single star, no matter how massive, controls only a tiny region of space. Its gravitational influence fades quickly with distance. Beyond a few light years, its pull becomes negligible compared to the combined influence of the galaxy. This is the first lesson in scale. Mass concentrates locally, but structure requires mass on larger scales. A star forms when gravity collapses a cloud of gas. That cloud was once part of something larger, a molecular cloud inside a galaxy. The star does not exist independently of that larger structure. Even the most massive star ever formed is still just one unit inside a much greater gravitational system, and stars do not dominate the mass of the universe. Most of the matter inside a galaxy is not in stars. It is in dark matter halos extending far beyond the visible disk. The luminous sphere of a star is just the visible tip of a much deeper gravitational iceberg. Imagine replacing every star in the night sky with black spheres of equal mass, but no light. The gravitational structure of the universe would barely change, because the stars are not what hold the cosmic web together. They are byproducts. They are temporary nodes in a much larger gravitational pattern. Even supermassive stars, those that briefly outshine entire galaxies, are ephemeral. They burn through their fuel in millions of years and collapse. Their mass redistributes. Their structure dissolves. On cosmic timescales, stars are fleeting. The most massive star that ever existed is insignificant compared to a galaxy. And a galaxy is insignificant compared to a cluster. When we look for the most massive structure in the universe, we cannot stop at stars. They are powerful locally, but they are fragments. To understand true mass on cosmic scales, we have to zoom out, far beyond any single star. Because the universe's largest structures are not built from one gravitational engine. They are built from billions of them working together. A galaxy is where gravity stops being local and starts becoming architectural. If a star is a single gravitational engine, a galaxy is a city of engines, billions of stars bound together, orbiting a shared center, embedded in something far larger than what we can see. Take the Milky Way. It spans roughly 100,000 light years across. That means if you traveled at the speed of light, the fastest speed possible in the universe, it would take you 100,000 years to cross it from one side to the other. Inside it are hundreds of billions of stars. each star with its own planets, each planet with its own potential chemistry, all of them orbiting a supermassive black hole at the center, Sagittarius A star, which itself contains about 4 million times the mass of the Sun. And yet, even that black hole is not the dominant source of mass in the galaxy. The visible disk, the glowing spiral arms, is only part of the story. Surrounding the Milky Way is a massive halo of dark matter extending far beyond the luminous stars. This halo may stretch out to more than 1 million light years. We cannot see it directly, but we can measure its presence through motion. Stars in the outer regions of the Milky Way orbit too fast to be held in place by visible matter alone. If only stars and gas were present, those outer stars should fly away into intergalactic space. They do not, which means something invisible is adding gravitational pull, dark matter. Estimates suggest that dark matter makes up roughly 85% of the total mass of the galaxy. That means everything we see, every glowing star, every nebula, every planet, is only a small fraction of what is actually there. The Milky Way's total mass is estimated to be around 1 to 2 trillion times the mass of the Sun. That is the mass of one galaxy. Now multiply that by billions. The observable universe contains hundreds of billions, possibly trillions of galaxies, each one embedded in its own dark matter halo, each one part of something larger. Galaxies are not randomly scattered, they group together. The Milky Way is part of a small collection called the Local Group. This group contains more than 50 galaxies, including Andromeda, which is roughly the same size as the Milky Way. The Local Group spans about 10 million light years. Already we are dealing with distances that make a single galaxy seem small. Inside a galaxy, stars orbit over hundreds of millions of years. Between galaxies, motion occurs over billions of years. Gravity operates more slowly at larger scales, but it still operates. Galaxies collide, they merge, they stretch and distort each other. The Milky Way and Andromeda are on a collision course. In about 4 billion years, they will merge into a single, larger galaxy. That merger will not be an explosion. It will be a slow gravitational dance lasting hundreds of millions of years. Stars will pass each other mostly without collision because space inside galaxies is mostly empty, but their orbits will be rearranged. The structure will change. Galaxies are dynamic. They grow by accretion. They absorb smaller galaxies. They feed their central black holes. And all of this is governed not by the visible spiral arms, but by the massive, invisible dark matter halo that defines their gravitational boundary. When astronomers map galaxies across vast distances, they do not see uniform distribution. They see clustering. Galaxies collect into larger and larger systems. That is the next level of scale. A galaxy is not the end of structure, it is the beginning of something bigger. Because when you zoom out far enough, galaxies themselves become points. Tiny nodes in a web so vast that even a trillion solar mass system like the Milky Way becomes insignificant. A galaxy feels enormous until you realize it is just one unit in a much larger gravitational architecture. And that architecture is where the search for the most massive structure truly begins. If a galaxy already feels incomprehensibly large, a galaxy cluster is where scale starts to break intuition. A galaxy is a gravitational system bound together by its own dark matter halo. But galaxy clusters are systems of galaxies, hundreds or even thousands of them, all bound together by an even larger gravitational structure. Imagine taking the Milky Way with its trillion solar mass halo and placing it in a region of space where it is not alone. Around it, dozens of galaxies, then hundreds, then thousands, all orbiting a shared gravitational center. That is a cluster. The local group, the small collection that contains the Milky Way and Andromeda, is not yet a true cluster. It is a small group. A cluster is far larger. Take something like the Coma cluster. It contains over 1,000 identified galaxies and spans about 20 million light-years across. Its total mass is estimated to be on the order of 10 to the 15th power solar masses. That is 1 quadrillion times the mass of the Sun. And again, visible matter is not the majority. Inside a galaxy cluster, most of the mass is dark matter. But there is another component that becomes significant at this scale: hot intracluster gas. Between galaxies inside a cluster, space is not empty. It is filled with extremely hot plasma, gas heated to tens of millions of degrees. This gas emits X-rays, making clusters visible to space telescopes operating in high-energy wavelengths. In fact, the mass of this hot gas can exceed the mass of all the stars in the cluster combined, and yet even that is still less than the dark matter content. So what holds a cluster together? Gravity. Not from a single galaxy, not from a central black hole, but from a massive, extended dark matter halo encompassing the entire cluster. Galaxies inside a cluster orbit at tremendous speeds, often over 1,000 kilometers per second. Without dark matter, they would escape. Clusters are gravitationally bound structures. That is important, because not all large-scale structures are bound. Some are just patterns. A galaxy cluster is truly held together by gravity. If you could stand outside a cluster and watch it over billions of years, you would see galaxies orbiting, interacting, merging. Some would fall toward the center. Others would be flung outward through gravitational encounters. Clusters are dynamic ecosystems on cosmic timescales, and clusters themselves are not evenly distributed. They sit at the intersections of filaments in the cosmic web. They are nodes. Where multiple filaments meet, mass accumulates. Gravity pulls matter along these filaments toward the densest points. Those densest points become clusters. If galaxies are cities of stars, clusters are continents of galaxies. But even clusters are not the final level, because clusters can group together into even larger patterns. When astronomers began mapping galaxy distributions across hundreds of millions of light years, they discovered something shocking. Clusters are not randomly placed. They align along enormous structures, walls and filaments stretching across space. The cluster is massive, incredibly massive. But it is still a component of something larger. When searching for the most massive structure in the universe, clusters are a critical step. They are among the most massive gravitationally bound systems that exist, but they are not the largest structures overall. Because beyond clusters, gravity becomes weaker relative to cosmic expansion, and yet structure continues. On scales so large that even a quadrillion solar mass cluster becomes just a point in a much bigger design. The most massive galaxy clusters are not just large collections of galaxies. They are the largest gravitationally bound objects in the universe. There is a difference between big and bound. A structure can span billions of light years and still not be gravitationally held together. Cosmic expansion can stretch matter apart faster than gravity can pull it inward. But a true cluster, the most massive kind, is a system where gravity has won locally against expansion. Consider a cluster with a mass of 1 quadrillion suns. That is 10 to the 15th solar masses. To understand that number, imagine stacking 1,000,000 Milky Way-sized galaxies together. That is roughly the mass scale we are talking about. Inside such a cluster, galaxies move at extreme velocities. A single galaxy can travel over 1,000 kilometers per second as it orbits the cluster's center of mass. That is more than 3 million kilometers per hour. These speeds tell us something crucial. Only an immense gravitational field could keep objects moving that fast from escaping. The visible galaxies are not enough to generate that gravity. The hot gas between galaxies is not enough either. Dark matter dominates the mass budget. In fact, in the largest known clusters, dark matter accounts for roughly 80 to 90% of the total mass. The galaxies are passengers. The gas is a secondary component. The real structure is invisible. Now imagine the gravitational field of such a cluster. It bends light dramatically. When distant galaxies sit behind these clusters, their images are distorted into arcs and rings due to gravitational lensing. Sometimes the bending is so extreme that multiple images of the same background galaxy appear. This is not artistic exaggeration. It is direct evidence of enormous mass warping spacetime. Clusters also shine in X-rays. The gas between galaxies is heated to tens of millions of degrees by gravitational compression. That gas emits high-energy radiation detectable by space telescopes. So the most massive clusters are not only gravitational giants, they are energetic. They glow in X-rays. They warp space. They dominate their local cosmic neighborhoods. And yet, even they are not static. Clusters grow. They pull in smaller groups of galaxies. They merge with other clusters. When two massive clusters collide, the event releases unimaginable energy. The gas clouds slam into each other, shock waves propagate across millions of light years, and dark matter halos pass through with minimal friction. One famous example of such a collision revealed something critical. Dark matter behaves differently from normal matter during impact. The gas slows down and heats up. The dark matter passes through almost unaffected. That separation gave astronomers one of the strongest confirmations that dark matter exists as a distinct component of reality. So when we talk about the most massive clusters, we are talking about laboratories of fundamental physics, structures that test our understanding of gravity itself. And yet, there is a limit. Clusters are massive, but they are not infinite. Beyond a certain scale, the expansion of the universe driven by dark energy prevents gravity from binding larger systems together. Clusters represent the upper bound of gravitational cohesion in the current era of the universe. They are the largest things that are truly held together. Beyond them, structures become looser. Filaments stretch, walls extend. But they are not gravitationally collapsing into a single object. So when searching for the most massive structure in the universe, we must make a distinction. If we mean the largest gravitationally bound system, then the answer lies with the most massive galaxy clusters. But if we mean the largest organized structure of matter, regardless of whether it is tightly bound, then we have to zoom out even further. And when we do, clusters shrink. They become nodes, points in a network so vast that even a quadrillion solar mass structure becomes just a junction in something far larger. This is where scale stops feeling physical and starts feeling abstract. When we move beyond individual clusters, the scale shifts from gravitational domination to cosmic architecture. Superclusters are not simply bigger clusters. They are collections of clusters. Clusters, groups, and individual galaxies arranged across hundreds of millions of light years in enormous patterns. But here is the critical difference. Most superclusters are not gravitationally bound as a single object. They are regions of enhanced density within the expanding universe. Gravity is still at work, but cosmic expansion has begun to compete on these scales. Take our own cosmic address. The Milky Way is part of the local group. The local group sits within a larger structure known as the Virgo cluster region. Zoom out further, and all of this belongs to a vast region called Laniakea Supercluster. Laniakea spans roughly 520 million light-years across. It contains around 100,000 galaxies. Its total mass is estimated to be on the order of 10 to the 17th solar masses, 100 quadrillion suns. And yet Laniakea is not a single collapsing object. It is defined by flow. Galaxies within Laniakea are moving toward a gravitational basin known as the Great Attractor, a massive concentration of matter hidden behind the plane of the Milky Way. Instead of orbiting a central point like galaxies in a cluster, galaxies in a supercluster drift along large-scale gravitational gradients. They flow. That is the defining characteristic of superclusters. They are not compact spheres. They are extended regions where matter slowly migrates toward denser nodes. If you could view a supercluster from outside over billions of years, you would see galaxies sliding along filaments like beads moving along invisible threads. Eventually, over extremely long timescales, some regions within a supercluster may collapse into tighter structures, but the entire supercluster will not. Dark energy, the mysterious force driving cosmic acceleration, prevents superclusters from becoming fully bound systems. This introduces a profound shift in scale. Galaxy clusters are gravitational islands. Superclusters are continental shelves. Beyond them, matter arranges itself into something even larger, the cosmic web. Superclusters are not isolated blobs. They connect to other superclusters through enormous filaments of galaxies and dark matter. These filaments stretch across hundreds of millions of light-years. Between them lie vast voids, regions of extremely low galaxy density spanning tens or even hundreds of millions of light-years. The universe on large scales does not resemble a random scatter of galaxies. It resembles foam, or a sponge, or a three-dimensional web. Superclusters occupy the densest nodes in this web, but even they are not the ultimate scale. Because when astronomers map the distribution of galaxies across billions of light-years, they find structures even larger than superclusters. Walls, filaments, gigantic arcs of galaxies stretching across unimaginable distances. At this level, the question of most massive becomes complicated. Are we asking about gravitational binding or total mass within a continuous structure? Superclusters contain enormous mass, but they are components of something even larger. And that larger pattern is where the search truly begins to challenge our understanding of cosmic scale. When astronomers first began mapping galaxies in 3 dimensions instead of just taking pictures of the sky, something unexpected emerged. The universe is not evenly sprinkled with galaxies. It is structured, not in neat spheres, not in tidy clusters alone, but in a vast interconnected network known as the cosmic web. If you zoom out far enough, hundreds of millions, then billions of light years, galaxies stop looking like isolated systems. They align. They trace enormous filaments stretching across space. These filaments intersect at dense nodes where galaxy clusters form. Between the filaments lie enormous voids, regions tens to hundreds of millions of light years wide containing very few galaxies. The cosmic web is the largest known pattern in the universe. It is not a single object. It is the framework. Imagine a 3-dimensional spider web the size of the observable universe. The threads are dark matter and gas. The knots are galaxy clusters. The small lights embedded along the threads are galaxies. The voids are empty bubbles expanding between them. This structure did not form randomly. It originated from tiny fluctuations in density shortly after the Big Bang. In the early universe, matter was nearly uniform, but not perfectly uniform. There were regions slightly denser than average. Gravity amplified those differences. Slightly denser regions attracted more matter. They became denser still. Over billions of years, those small fluctuations evolved into the vast filaments we observe today. Dark matter played the dominant role. Because dark matter does not interact with light, it began clumping earlier than normal matter. It formed the scaffolding first. Ordinary matter, gas, stars, galaxies, followed the gravitational blueprint set by dark matter. That is why when we look at large-scale galaxy maps, we see web-like patterns. We are seeing the visible matter tracing the invisible dark matter network. The cosmic web stretches across the observable universe. Filaments can span hundreds of millions of light years. Some structures within this web, sometimes called walls, extend even farther. And here the concept of most massive structure becomes difficult, because the cosmic web is not one continuous gravitationally bound object. It is a network. It is not collapsing into a single point. It is expanding along with the universe, yet it contains the vast majority of matter on the largest scales. The nodes, galaxy clusters, are gravitationally bound. The filaments are regions of higher density, but not necessarily bound as single entities. The voids expand faster than average because they contain less matter. This means the cosmic web evolves over time. Clusters grow at the nodes. Filaments stretch thinner. Voids expand larger. Dark energy accelerates this process, slowly isolating clusters from one another. In the far future, distant filaments will move beyond our cosmic horizon. The web will fragment from our perspective. But right now, on the largest scales we can observe, the cosmic web represents the dominant structure of matter in the universe. It is larger than any cluster, larger than any supercluster. It is the pattern that contains them all. When searching for the most massive structure, we may not find a single object. We may instead find a network, a vast gravitational lattice extending across billions of light years. A structure so large that no single galaxy, cluster, or supercluster defines it. The web itself is the architecture, And within that architecture, certain regions stand out as extraordinarily massive, enormous walls and filaments that push the limits of how large a structure can be. Those are where scale begins to challenge cosmology itself. When astronomers talk about structures beyond clusters and superclusters, they eventually arrive at something that challenges intuition. Enormous walls of galaxies stretching across distances so vast that even the word structure starts to feel insufficient. One of the most famous of these is the Sloan Great Wall, a colossal filamentary complex discovered through large-scale redshift surveys. It spans roughly 1.4 billion light-years. That number is not just large. It represents a significant fraction of the observable universe's radius. To grasp that scale, consider that the Milky Way is about 100,000 light-years across. You could line up 14,000 Milky Ways side by side and still not match the length of this wall, and the Milky Way itself would be just one tiny luminous speck embedded somewhere within that expanse. These walls are not solid objects like a planet or a star. They are regions where galaxy density is significantly higher than average, arranged along immense filaments of dark matter. When astronomers map the three-dimensional distribution of galaxies using redshift, measuring how much their light has been stretched by cosmic expansion, they effectively construct a depth map of the universe. What emerges is not randomness, but geometry. Arcs, sheets, chains of galaxies forming patterns that resemble foam bubbles or a neural network. The Sloan Great Wall is one of the most dramatic examples of this geometry, a testament to how small primordial fluctuations grew into continent-sized structures of matter under gravity's influence. Yet even more extreme candidates have been proposed. The Hercules Corona Borealis Great Wall is estimated to span close to 10 billion light-years, making it potentially the largest known coherent structure in the observable universe. Its existence was inferred from the distribution of gamma-ray bursts, powerful explosions associated with the deaths of massive stars or the mergers of compact objects. By mapping where these bursts occur across cosmic time, astronomers noticed a clustering that suggested a structure of staggering scale. 10 billion light-years is nearly 1/4 of the diameter of the observable universe. At that size, the question is no longer just about mass. It becomes about cosmology itself. Because the cosmological principle, one of the foundational assumptions of modern cosmology, states that on sufficiently large scales, the universe should be homogeneous and isotropic. In simple terms, if you zoom out far enough, matter should look evenly distributed. No preferred directions, no massive asymmetries. But when structures approach billions of light-years in extent, they begin to test that principle. Are these truly coherent structures, or are we seeing statistical clustering within a fundamentally uniform background? Is the universe smooth at the largest scales, or does it contain patterns larger than our models predict? To answer that, we need to think in terms of scale-dependent behavior. On small scales, galaxies, clusters, gravity dominates. On intermediate scales, superclusters and filaments, gravity competes with expansion. On the largest scales, billions of light-years, cosmic expansion driven by dark energy becomes dominant. Structures cannot grow indefinitely because expansion stretches space itself. The growth of structure slowed dramatically once dark energy began dominating the universe's energy density around 5 billion years ago. That means the largest walls and filaments we observe today are fossil imprints of earlier epochs, when matter density was higher and gravity had more influence. The mass contained within these structures is extraordinary. Even though they are not gravitationally bound as a single object, the cumulative mass of galaxies, dark matter, and intergalactic gas within a wall, like the Sloan Great Wall, reaches unimaginable levels, potentially exceeding 10 to the power of 17 or 10 to the power of 18 solar masses when integrated across the entire filamentary complex. But the key is that this mass is distributed across enormous distances. The average density is still only slightly above the cosmic mean. That is why such structures do not collapse into a single superobject. They are overdensities, not compact bodies. And this leads to a subtle but crucial distinction in the search for the most massive structure. If we define structure as something gravitationally bound, then massive galaxy clusters win. But if we define it as the largest coherent arrangement of matter, then these great walls and filaments become candidates. The difficulty lies in defining coherence. A wall stretching 1.4 billion light-years is not a solid slab of galaxies. It is a pattern, a region where galaxies are more common, arranged along dark matter filaments, separated by vast cosmic voids. These voids are equally important. They can span hundreds of millions of light-years and contain very few galaxies. They are not truly empty. Dark matter and diffuse gas still exist within them, but their density is far below average. As the universe expands, voids expand faster than denser regions. Over billions of years, voids grow larger while filaments thin out. This enhances the contrast of the cosmic web. If we step back even further and imagine observing the universe from an impossible vantage point outside it, what we would see is not a collection of separate giant walls. We would see a continuous cosmic web stretching across the observable horizon. Individual walls like the Sloan Great Wall are simply prominent sections of that web. Regions where density fluctuations were amplified more strongly. So when we ask about the most massive structure, we may ultimately be confronting the limits of categorization. Is it a cluster, the most massive gravitationally bound object? Is it a supercluster, a vast flow-defined region? Is it a wall, a filamentary overdensity spanning billions of light-years? Or is it the cosmic web itself, the entire large-scale distribution of matter shaped by gravity and expansion? At the largest scale accessible to observation, the cosmic web represents the ultimate structure of matter. It is not bound into a single object. It is not collapsing. It is expanding along with the universe. But it contains nearly all the mass we can observe: dark matter, halos, galaxies, gas, clusters, arranged into an intricate network that defines the universe's architecture. And beyond that scale lies a boundary: the observable universe itself. Roughly 93 billion light-years in diameter, it represents the limit of what light has had time to reach us since the Big Bang. Beyond it, there may be more web, more walls, more clusters, or complete homogeneity. We do not know. What we do know is this: the most massive structure in the universe is not a single shining object. It is a pattern, a network, a gravitational fossil record stretching across billions of light-years, shaped by quantum fluctuations in the first fractions of a second after the Big Bang, amplified by gravity over 13.8 billion years, and now slowly being pulled apart by cosmic acceleration. At that scale, the concept of massive stops being about weight. It becomes about architecture, and we are inside it. If we continue climbing outward in scale, beyond walls and filaments, we eventually reach a boundary that is not defined by gravity, but by light, the observable universe. This is not the entire universe. It is the portion from which light has had time to reach us since the Big Bang, approximately 13.8 billion years ago. Because space itself has been expanding during that time, the radius of the observable universe is not 13.8 billion light-years, but about 46.5 billion light-years in every direction. That makes its diameter roughly 93 billion light-years. Everything we have discussed, stars, galaxies, clusters, superclusters, walls, the cosmic web, exists inside this sphere. If we integrate all the matter inside this volume, including dark matter and normal matter, the total mass becomes almost incomprehensible. Estimates suggest that the observable universe contains on the order of 10 to the power of 23 stars. If the average star is roughly comparable in mass to the Sun, that alone gives around 10 to the power of 23 solar masses. But stars are only a fraction of the total mass. Including dark matter increases the total matter content by roughly a factor of 6. We are now talking about 10 to the power of 24 to 10 to the power of 25 solar masses of matter within the observable universe. That number is so large it no longer behaves like a countable quantity in human terms. It becomes statistical, a smooth distribution of mass energy across cosmic scales. But here is the crucial distinction. The observable universe is not a gravitationally bound structure. It is not an object. It is a horizon. It is defined by the speed of light and the age of the universe. Beyond that horizon, there may be more structure identical to what we see, or the universe may curve differently, or physical constants may vary. We do not know. The observable universe is not a physical wall. It is a limit of information. So can we call it the most massive structure? In one sense, yes. It contains all the matter we can observe. It is the largest coherent region of space-time we can measure directly. But in another sense, no. Because it is not held together. It is expanding. Distant galaxies at the edge of the observable universe are receding from us at speeds exceeding the speed of light due to cosmic expansion. Not because they are moving through space faster than light, but because space itself is stretching. Gravity binds galaxies. It binds clusters. It partially binds superclusters. But it does not bind the observable universe as a whole. Dark energy dominates on the largest scales. It accelerates expansion. It ensures that over extremely long timescales, distant clusters will move beyond our horizon, leaving only our local gravitational island visible. In trillions of years, if intelligent observers still exist in the Milky Way's merged descendant galaxy, they will see a dark, empty sky. The cosmic web beyond the local group will have redshifted beyond detectability. The observable universe will shrink to a single gravitationally bound remnant, which means that the largest structure we can currently observe is temporary. Our view of the cosmic web is time-dependent. Right now, we live in an era where we can still see the large-scale structure of the universe. We can map filaments across billions of light years. We can identify great walls and superclusters. But this is a brief window in cosmic history. On the largest scales, the universe approaches homogeneity. When astronomers average galaxy density over volumes larger than about 300 million light-years, fluctuations smooth out. The universe begins to look statistically uniform. This supports the cosmological principle. Even though we see enormous walls and voids, they are fluctuations around an average density. No known structure dominates the entire observable universe. Even the largest proposed walls occupy only a fraction of it. So when we ask about the most massive structure, we are navigating definitions. If we mean the largest gravitationally bound object, massive galaxy clusters. If we mean the largest coherent over density, great walls like Sloan or Hercules' Corona Borealis. If we mean the total matter content within a causal boundary, the observable universe itself. But perhaps the most accurate answer is this. The most massive structure is not a single object. It is the large-scale distribution of matter across the observable universe, the cosmic web, and we are embedded within one of its minor filaments. The Milky Way is not central. The local group is not special. Even Laniakea is just a small flow basin in a much larger network. When you zoom out far enough, identity dissolves into structure. The most massive structure in the universe is not something you can isolate with a circle. It is the pattern of matter shaped by gravity across billions of light years. A pattern born from quantum fluctuations in the first fractions of a second after the Big Bang, amplified for 13.8 billion years, and still evolving under the tension between gravity and expansion. To understand how the largest structures in the universe formed, we have to go back to a time when there were no galaxies, no stars, no clusters, no filaments. A time when the universe was nearly uniform, almost perfectly smooth, filled with hot plasma and radiation, expanding rapidly from an incomprehensibly dense origin. And yet not perfectly smooth. That imperfection is everything. In the first tiny fraction of a second after the Big Bang, during a phase known as cosmic inflation, quantum fluctuations, microscopic variations in energy at subatomic scales, were stretched to astronomical sizes. Inflation expanded space so violently that fluctuations smaller than a proton were blown up to scales larger than galaxies. These fluctuations were random, but they were real. And once inflation ended, they remained imprinted in the fabric of space-time as tiny variations in density. The early universe was about 99.999% uniform. That sounds smooth, but that remaining 0.001% difference in density is what ultimately created every structure we see today. Regions that were slightly denser than average exerted slightly stronger gravitational pull. As the universe expanded and cooled, gravity began amplifying those differences. Matter flowed slowly toward the denser regions. Over millions of years, those regions became denser still. Dark matter played the decisive role in this process. Unlike normal matter, which was tightly coupled to radiation in the early universe, dark matter did not interact with light. It began collapsing into clumps earlier than ordinary matter could. It formed gravitational wells first. Normal matter later fell into those wells once the universe cooled enough for atoms to form and radiation pressure decreased. What we observe today in the cosmic web is essentially a fossil record of those primordial fluctuations. The distribution of galaxies across billions of light years still reflects the statistical imprint of quantum noise stretched during inflation. The pattern is not arbitrary. It carries encoded information about the earliest moments of the universe. When we examine the cosmic microwave background, the afterglow radiation from about 380,000 years after the Big Bang, we see tiny temperature fluctuations. These correspond directly to density variations in the early universe. The amplitude of those fluctuations matches remarkably well with the large-scale distribution of galaxies we observe today. It is a direct link between quantum mechanics and galaxy clusters. The growth of structure followed a hierarchical pattern. Small overdensities collapsed first, forming the earliest dark matter halos. Gas fell into these halos, cooled, and formed the first stars. Small galaxies merged into larger galaxies. Galaxies merged into groups. Groups merged into clusters. Clusters aligned along filaments. Filaments intersected to form nodes in the cosmic web. This process took billions of years. At early times, gravity dominated. The universe was denser, so matter could collapse more efficiently. But as the universe expanded, its average density decreased. Eventually, dark energy began to dominate the large-scale dynamics of expansion. This occurred roughly 5 billion years ago. Since then, the expansion of the universe has accelerated. This acceleration suppresses the growth of new large-scale structures. Gravity still binds existing clusters and galaxies, but on very large scales, expansion pulls matter apart faster than gravity can gather it. That means the cosmic web we see today is close to its maximum extent in terms of structural growth. Filaments will not grow significantly thicker. Clusters will not combine into ever larger bound systems indefinitely. In that sense, the largest structures in the universe are relics of a past era, when gravity had more influence relative to expansion. Simulations of cosmic structure formation confirm this. When cosmologists input the laws of gravity, dark matter properties, and the measured amplitude of primordial fluctuations into supercomputers, the result is astonishing. The simulations generate filamentary networks almost identical to the observed cosmic web. Nodes form where filaments intersect. Voids expand between them. The match between simulation and observation is one of the strongest validations of modern cosmology. And what these simulations reveal is that structure formation is self-similar across scales. Small-scale patterns echo larger-scale ones. Dark matter halos merge into bigger halos. Filaments connect clusters in a repeating geometric hierarchy. But there is a limit. Because space itself is expanding, there is a maximum scale beyond which gravity cannot organize matter into coherent bound structures. That limit is determined by the balance between gravitational attraction and the repulsive effect associated with dark energy. So when we search for the most massive structure in the universe, we are really asking, how far did gravity manage to impose order before expansion took over? The answer lies in those immense walls and filaments stretching across billions of light years. They represent the largest overdensities that gravity was able to amplify significantly before dark energy slowed the process. And beyond that, on even larger scales, the universe approaches statistical uniformity again. The largest structures are not isolated monuments floating in empty space. They are peaks in a vast expanding landscape. They were born from quantum fluctuations, shaped by gravity, limited by dark energy, and measured today by mapping galaxies across unimaginable distances. When we talk about the most massive structure in the universe, we are ultimately talking about the amplified imprint of quantum noise stretched across cosmic history, forming the web in which every galaxy, every star, and every observer resides. To truly understand the largest structures in the universe, we need to shift from imagination to measurement. The cosmic web is not something we see directly with our eyes. It is reconstructed through surveys, redshifts, gravitational lensing, statistical modeling, and enormous data sets collected over decades. The universe does not come with labeled boundaries. We infer structure by mapping positions and distances of millions of galaxies in 3 dimensions. Distance in cosmology is not simple. We cannot stretch a measuring tape across billions of light years. Instead, we rely on redshift, the stretching of light due to cosmic expansion. When a galaxy moves away from us, its light shifts toward longer wavelengths. The amount of this shift tells us how much the universe has expanded since the light was emitted. From that, we estimate distance. Large surveys like the Sloan Digital Sky Survey mapped millions of galaxies across large portions of the sky, constructing 3-dimensional maps of their positions. When plotted, galaxies are not randomly scattered points. They form chains, arcs, clusters, visible threads of a deeper structure. These maps revealed the Sloan Great Wall and other massive filaments, not as artistic interpretations, but as statistical realities. But even galaxy surveys only show the visible matter. Most of the mass is dark matter, invisible to telescopes. To trace that, astronomers rely on gravitational lensing. Massive structures bend light from more distant objects. By measuring distortions in the shapes of background galaxies, scientists reconstruct the mass distribution in foreground regions. This technique allows us to map dark matter directly, not by seeing it, but by measuring its gravitational influence. When lensing maps are compared with galaxy maps, they align. Galaxies sit within dense dark matter filaments. Clusters coincide with peaks in dark matter density. The visible structure traces the invisible skeleton. On even larger scales, cosmologists use statistical tools like the 2-point correlation function to quantify how galaxies cluster relative to random distributions. These methods confirm that structure exists up to certain scales, beyond which matter becomes statistically uniform. That threshold matters. Observations suggest that on scales larger than roughly 300 million light-years, the universe begins to smooth out. Density fluctuations become small relative to the mean. This supports the cosmological principle. The universe is homogeneous and isotropic on sufficiently large scales. So how do we reconcile enormous structures like the Hercules Corona Borealis Great Wall, spanning billions of light-years, with the idea of large-scale uniformity? The answer lies in interpretation. Some of these walls may not be single coherent physical structures in the way a galaxy cluster is. Instead, they may represent alignments of multiple filaments or statistical clustering within a larger homogeneous background. Our observational perspective also matters. We see a 3-dimensional projection limited by our position and the finite speed of light. Apparent structures may partly reflect selection effects or sampling limits. Modern cosmology addresses this with simulations. Supercomputers model billions of particles representing dark matter, evolving them under gravity across cosmic time. The results produce web-like patterns nearly identical to what surveys observe. By comparing simulations to real data, cosmologists determine whether observed structures are consistent with standard cosmological models. So far, even the largest known walls can be accommodated within the lambda CDM model, the standard cosmological framework including dark energy, lambda, and cold dark matter, CDM. That means while these structures are enormous, they do not necessarily violate fundamental principles, but they push limits. They test the scale at which homogeneity truly emerges. They refine our understanding of how density fluctuations grow. They constrain dark matter properties. They even provide indirect tests of dark energy's influence. Measurement also reveals something profound. The largest structures are not static in time. When we look far into space, we look back in time. A galaxy 1 billion light-years away is seen as it was 1 billion years ago. A wall 10 billion light-years away is seen when the universe was much younger. Structure evolves across cosmic history. Early in the universe, density fluctuations were smaller. The cosmic web was less pronounced. As time progressed, gravity amplified structure. But now, as dark energy accelerates expansion, growth slows. This means that the most massive structures we observe today are snapshots of a universe transitioning from gravity-dominated growth to expansion-dominated dilution. We are observing structure near its maximum complexity. In trillions of years, distant filaments will slip beyond our horizon. The observable universe will shrink to a single gravitationally bound remnant, likely the merged Milky Way Andromeda galaxy. Future observers would not detect the cosmic web at all. They would infer a static, isolated universe. Right now, we are uniquely positioned to see the largest structures in existence. Through redshift mapping, gravitational lensing, statistical analysis, and simulation comparison, we have reconstructed a three-dimensional map of matter stretching across tens of billions of light-years. And what that map shows is not a random scattering of galaxies. It shows order, scale-dependent order, hierarchy born from quantum fluctuations, a web of matter spanning the observable cosmos. When we ask what the most massive structure in the universe is, we are not simply looking for the biggest object. We are confronting the architecture of space itself, revealed through measurement, mathematics, and the bending of light across billions of years. At some point in this climb through scale, the question itself begins to change. We started by asking what the most massive structure in the universe is. But now we have to ask something more precise. What do we even mean by a structure? A galaxy is a structure because it is gravitationally bound. Its stars orbit a common center. Its dark matter halo encloses it. It behaves as a single dynamical system. A galaxy cluster is also a structure. Hundreds or thousands of galaxies orbit within a shared gravitational well. Remove one galaxy, and the cluster remains. The system persists as a cohesive entity. But when we move to superclusters and walls, coherence weakens. These are not tightly bound systems. They are regions of higher density within an expanding universe. Their galaxies are not orbiting a central point in a stable configuration. many are slowly drifting apart under cosmic expansion. So is a wall truly a structure, or is it a temporary alignment within a larger statistical pattern? To answer that, we need to think in terms of gravitational binding energy versus expansion energy. On smaller scales, gravity overcomes expansion. On larger scales, expansion dominates. There is a threshold scale, sometimes called the turnaround radius, beyond which matter cannot remain gravitationally bound as a single system in a universe dominated by dark energy. In our current cosmological model, that maximum bound scale is on the order of a few 100 million light years. Structures significantly larger than this are not collapsing into a single object. They are slowly being stretched apart. This means that the truly largest gravitationally bound objects in the universe are galaxy clusters, perhaps up to a few tens of millions of light years across. Everything beyond that is part of a larger pattern but not a bound object, and yet the pattern itself contains enormous mass. If you take a filament stretching 1 billion light years and integrate all the matter within it, the total mass is extraordinary, perhaps exceeding that of any individual cluster by orders of magnitude. But that mass is distributed across a vast distance. It does not act as a single gravitational unit. This distinction matters because physics behaves differently in bound versus unbound systems. Bound systems can collapse, merge, oscillate. Unbound overdensities will eventually be diluted by expansion. Over cosmic time, dark energy ensures that large-scale structure formation slows and eventually stops. In the far future, clusters will remain bound internally, but superclusters will fragment. Filaments will thin. Voids will dominate. So when we speak of the most massive structure in the universe, we are navigating between definitions. If we mean the largest gravitationally bound object, the answer lies with the most massive galaxy clusters. If we mean the largest coherent overdensity visible in the cosmic web, then massive walls and filaments qualify. If we mean the total organized distribution of matter across cosmic scales, then the cosmic web itself is the structure. And if we stretch the definition further, the observable universe becomes the largest mass-containing region we can define. But the observable universe is not held together. It is not collapsing. It is not a structure in the traditional sense. It is a causal horizon. So perhaps the most accurate way to phrase the answer is this. The universe does not contain a single largest object in the way a planet contains mountains or oceans. Instead, it contains a hierarchy of structures, each defined by scale-dependent physics. Gravity builds small structures. Gravity and expansion together shape medium structures. Dark energy limits the growth of the largest patterns. The most massive structure is not a monolithic entity. It is a level in a hierarchy. And that hierarchy emerges naturally from initial conditions set nearly 14 billion years ago. The deeper truth is that structure in the universe is statistical. It arises from fluctuations amplified over time. It does not require intentional design. It is the inevitable consequence of gravity acting on uneven density in an expanding space. And when we zoom out far enough, beyond clusters, beyond walls, beyond even the cosmic web, we find that the universe begins to look smooth again. On the largest scales, the average density becomes uniform. There is no edge to a wall, no center to the web, just a near homogeneous sea of matter energy. So the search for the most massive structure ultimately teaches us something unexpected. The universe builds complexity up to a limit. Beyond that limit, it returns to simplicity, and we live in between. To push this even further, we need to confront a difficult idea. Maybe the universe does not have a single, most massive structure at all in the way our intuition wants it to. Human thinking prefers hierarchy with a final boss at the top, the tallest mountain, the biggest animal, the largest building. But cosmic structure is not arranged like a pyramid with a single apex. It is arranged like a fractal that gradually smooths out. On small scales, gravity creates clear boundaries. A star is a star. A galaxy is a galaxy. A cluster is a cluster. These are physically meaningful systems with definable edges, measurable binding energies, and internal dynamics that distinguish them from their surroundings. But once we step beyond a few 100 million light years, edges blur. Density contrasts decrease. Matter becomes more evenly distributed. The cosmic web looks dramatic when mapped visually, but mathematically it is a pattern of overdensities embedded in an almost uniform background. The amplitude of fluctuation shrinks as you average over larger volumes. This is why cosmologists use statistical measures rather than object catalogs at the largest scales. Instead of asking, where does this structure begin and end, they ask, what is the variance of density on this scale? Structure becomes a question of probability, not boundaries. The early universe gives us the key. During inflation, quantum fluctuations were nearly scale invariant. That means perturbations existed on many different length scales with roughly similar relative amplitudes. Gravity amplified these fluctuations hierarchically. Small scales collapsed first. Larger scales followed more slowly. But the universe also expanded continuously. As it expanded, the overall density dropped. As density dropped, gravity's ability to create ever larger bound systems weakened. Then dark energy emerged as the dominant factor, accelerating expansion and effectively freezing large-scale structure growth. So there is a maximum meaningful scale of gravitational organization. Beyond that, fluctuations remain linear. They do not collapse into non-linear bound systems. That maximum scale defines the upper bound for what we might reasonably call a structure, and that scale is much smaller than the observable universe. So when people refer to the Hercules Corona Borealis Great Wall as the largest structure in the universe, what they often mean is the largest observed overdensity or coherent alignment within current surveys. But it is not a single gravitationally bound object spanning 10 billion light years. It is a statistical feature in the distribution of galaxies and gamma-ray bursts. It is enormous, but it is not solid. It is not a cosmic slab of matter moving as one. It is a region where density happened to be slightly above average over a vast area. The same is true for other walls and filaments. They are extreme examples of clustering. They do not contradict homogeneity on sufficiently large scales. They are fluctuations within it. This brings us to an important conceptual shift. The universe does not have a largest thing. It has a largest scale of significant inhomogeneity. Beyond that scale, matter averages out. The cosmic web is dramatic when seen up close, like looking at the structure of foam bubbles. But step back far enough, and the foam becomes a smooth surface. So the most massive structure may not be an object at all. It may be the pattern of large-scale structure itself, the web-like distribution of matter across the observable cosmos. And that web is not static, it is dynamic. Clusters continue to merge, filaments continue to thin, voids continue to expand. In the far future, dark energy will isolate clusters into gravitational islands. The web will fragment. Observers in those distant epochs will not see vast interconnected structures. They will see only their local cluster surrounded by darkness. From their perspective, the universe will appear smaller, simpler, devoid of large-scale structure. We live in a privileged epoch, an era when structure is still visible across billions of light-years, an era when gravity's imprint is still readable across the sky. When we ask what the most massive structure in the universe is, we are really asking how far gravity managed to imprint its pattern before expansion diluted it. The answer is written in filaments stretching across hundreds of millions to billions of light years. But beyond that, the universe becomes smooth again. No ultimate wall, no final megastructure. Just the gradual fading of contrast into cosmic uniformity. And that might be the most profound conclusion of all. The universe builds vast structures, but it never builds a final one. If we keep climbing outward in scale, the question begins to dissolve into something even stranger. Maybe the largest structure is not made of galaxies at all, but of space-time itself. Because every structure we've discussed, stars, galaxies, clusters, filaments, exist inside the geometry of the universe. And that geometry is not static. It expands, it curves, it evolves. Mass bends space-time. That's Einstein's general relativity. But on the largest scales, space-time also dictates how mass can organize. The cosmic web is not floating inside a neutral background. It is embedded in an expanding metric. Space itself stretches. This means that the largest structure is inseparable from expansion. When we talk about the observable universe being 93 billion light-years across, we are not describing a physical shell. We are describing the maximum region from which light has reached us. Beyond that boundary, there may be more cosmic web, more clusters, more filaments, possibly infinitely more. If the universe is spatially infinite, which current observations allow, then the cosmic web might extend without bound. There may be no largest structure at all. Every wall we identify could simply be a local maximum within an endless pattern. And that introduces a radical idea. If the universe is infinite, then somewhere, far beyond our observable horizon, there are structures larger than anything we have detected. Not because physics allows bigger bound systems, but because statistical fluctuations on arbitrarily large scales could occur given infinite volume. In such a universe, largest becomes meaningless. There would always be something larger beyond our view. But even within the observable universe, we can estimate something profound: the mass energy content of everything we can see. Roughly 5% ordinary matter, 27% dark matter, 68% dark energy. Dark energy is not clustered into structures. It is uniform. It fills space evenly, which means the majority of the universe's energy content does not participate in structure formation at all. If we are counting total mass energy, then dark energy dominates. And dark energy is not organized into clusters or walls. It is smooth. So ironically, the largest component of the universe is the least structured. Matter builds filaments. Dark energy erases them. Over time, dark energy will win. Clusters will remain bound internally. but they will drift apart from one another. The cosmic web will thin. The largest structures will become isolated nodes surrounded by expanding void. In trillions of years, observers in a future galaxy will not detect the cosmic microwave background. It will be redshifted beyond detectability. They will not see distant clusters. Expansion will carry them beyond the horizon. From that perspective, the universe will appear static and small. All evidence of the largest structures will be gone, which means the existence of massive walls and filaments is temporary. The largest structures in the universe are epoch-dependent. They exist now because we are in a transitional phase between matter-dominated and dark energy-dominated expansion. Before galaxies formed, there were no walls. After expansion isolates clusters completely, there will effectively be no visible web. We live in the narrow window when structure is visible at its maximum extent. So perhaps the most massive structure is not a single wall or cluster. Perhaps it is the large-scale distribution of matter during this era of cosmic history. A network of dark matter filaments stretching across billions of light years. Clusters weighing quadrillions of solar masses sitting at their intersections. Voids expanding between them, and all of it slowly being stretched apart. When you zoom out far enough, structure becomes time-dependent. Mass organizes, then disperses. Gravity gathers, then dark energy separates. The universe never builds a final monument. It builds patterns that evolve. The most massive structure we can identify today is part of that evolving pattern, a web suspended between gravitational collapse and cosmic acceleration. And it will not last forever. If we want to answer the question with maximum precision, we have to separate three different meanings of largest and most massive, because at cosmic scale, those words stop being interchangeable. First, the largest gravitationally bound structure. This is the cleanest definition physically. A bound structure is one whose self-gravity overcomes cosmic expansion. Its parts orbit a shared center. Its total energy is negative. Remove cosmic expansion entirely, and it would still hold together. Under that definition, the winners are the most massive galaxy clusters. Systems with masses approaching or exceeding 10 to the power of 15 solar masses. Regions where hundreds or thousands of galaxies move at thousands of kilometers per second, trapped in a shared dark matter halo. These clusters are genuine physical objects in the dynamical sense. They are islands of gravity resisting expansion. Second, the largest coherent over density. This includes immense filaments and walls stretching across hundreds of millions or even billions of light years. The Sloan Great Wall, the Hercules Corona Borealis alignment. These contain enormous cumulative mass, sometimes vastly exceeding any single cluster, but they are not bound into one collapsing body. Their coherence is statistical, not dynamical. They are peaks in the density field, not self-contained gravitational systems. Third, the largest causal structure. That is the observable universe itself. Everything whose light has reached us since the Big Bang. Its total matter content dwarfs any individual wall or filament, but it is not bound. It is not collapsing. It is expanding. It is a horizon, not a gravitational object. Now, here is where it becomes subtle. Mass is not evenly distributed inside these scales. Dark matter halos concentrate mass at cluster nodes. Filaments contain lower density but extend far longer distances. Voids contain very little matter but dominate volume. If you integrate total mass over a sufficiently large region, the result scales with volume. So any sufficiently large region will contain more mass than any smaller one. This means there is no upper bound on total mass if the universe is spatially infinite. So the real physical upper limit must come from dynamical cohesion, and that is where dark energy imposes a ceiling. In a universe dominated by dark energy, there is a maximum scale at which gravity can overcome expansion. Structures larger than that scale cannot collapse into bound systems. That scale is sometimes referred to as the maximum turnaround radius. For our cosmological parameters, that radius is on the order of a few tens of millions of light years, which means that anything significantly larger than that cannot ever become a single bound object. Clusters approach that limit. Superclusters exceed it. Walls vastly exceed it. So the largest bound structures are clusters. Everything larger is a pattern. This leads to an uncomfortable but important conclusion. The universe does not contain a single, ultimate, most massive object that dominates everything else. It contains a hierarchy of structures, and that hierarchy flattens out at large scales. Matter becomes homogeneous beyond several 100 million light years. Density fluctuations average out. The cosmic web is dramatic, but it is not infinite in contrast. Its peaks are finite. Its troughs are finite. Beyond a certain averaging scale, the universe becomes smooth, which means the search for the most massive structure is less about finding a final answer and more about understanding where gravitational organization stops being meaningful. We can say, the most massive bound objects are galaxy clusters. The largest visible over densities are cosmic walls. The largest mass-containing region we can define is the observable universe. And beyond that, there may be more universe, perhaps infinitely more, repeating similar patterns on unimaginably larger scales. But there is no ultimate cosmic monument, no final megastructure towering above all others. Instead, there is scale-dependent organization shaped by gravity and limited by expansion. The largest structures are not singular. They are emergent. And they exist only because the universe is young enough that gravity still leaves visible imprints across billions of light years. In the far future, even those imprints will fade. Clusters will remain. The web will dissolve. And the concept of largest structure will shrink to whatever gravitational island survives the longest. Right now, we live in the era when the universe is most structured, and that may be the most massive truth of all. If we continue this climb without reducing it to headlines, we reach something even more unsettling. The largest structure in the universe may not be defined by mass alone, but by information. Because structure is not just matter arranged in space. It is matter arranged non-randomly. When cosmologists map billions of galaxies, they are not only measuring mass density. They are measuring correlation, how likely one galaxy is to exist near another at a given distance. Structure is fundamentally about deviation from randomness. On small scales, deviation is extreme. Stars are tightly bound into galaxies. Galaxies cluster into dense groups. Clusters exhibit strong gravitational coherence. On intermediate scales, deviation weakens but persists. Filaments show enhanced density relative to voids. Walls trace regions of correlated galaxy distribution, but on the largest scales, correlation fades. Beyond a few 100 million light-years, galaxy positions approach statistical uniformity. Fluctuations remain, but they are small compared to the mean density. This is not a philosophical claim. It is measurable. The power spectrum of density fluctuations, essentially a graph describing how strongly matter clusters at different scales, shows that clustering amplitude decreases as scale increases. At sufficiently large wavelengths, fluctuations become linear. They no longer grow dramatically over time. This tells us something profound. There is a largest meaningful scale of nonlinear structure. Gravity amplified density differences until dark energy suppressed further growth. Everything beyond that is smooth to first approximation. This means that even if we discover ever larger walls, they do not represent a fundamentally new regime of physics. They are statistical features within an underlying nearly uniform distribution. The cosmic web is a frozen echo of early quantum fluctuations, and those fluctuations were nearly scale invariant but finite in amplitude. Fluctuations had been slightly larger in size, the universe would have collapsed. If the early fluctuations had been slightly smaller in size, the universe would have never formed. The size of the largest structures is not arbitrary. It is constrained by initial conditions, constrained by inflation, constrained by matter density, constrained by dark energy. If the early fluctuations had been slightly larger in amplitude, structure would have grown more aggressively. We might see even denser, more dramatic walls. If fluctuations had been smaller, structure would be weaker. The universe might look almost uniform, even on smaller scales. So the scale of the largest structures encodes information about the earliest moments of cosmic history. The web's geometry is a fossil. Its size distribution reflects inflationary physics. When we simulate the universe from initial conditions measured in the cosmic microwave background, we reproduce filament lengths, cluster masses, void sizes. That is not coincidence, it is causation. The largest structure is therefore not just a mass concentration, it is a boundary condition, a record of how far gravity was allowed to sculpt matter before expansion diluted the sculpting process. And here is the final twist in scale. If inflation lasted slightly longer than the minimum required, the universe could be vastly larger than the observable region, perhaps exponentially larger. In that case, what we see as the cosmic web may be a tiny patch of a much larger structure that continues beyond our horizon. But we cannot observe beyond that boundary. Our observable universe is a sample. Within that sample, we detect walls billions of light-years long. But statistically, there may be even larger over densities beyond our reach, or there may be none. The observable universe defines the limit of empirical structure. Beyond it lies speculation. So when we ask what the most massive structure in the universe is, the most honest answer may be conditional. Within the observable universe, the largest coherent patterns are vast galaxy walls and filaments embedded in the cosmic web. Within gravitationally bound systems, massive galaxy clusters dominate. Within total mass energy content, the observable universe itself contains the most matter we can define. But beyond our horizon, the story may continue in ways we cannot measure. The universe does not provide a neatly labeled maximum. It provides a hierarchy shaped by initial fluctuations, amplified by gravity, limited by dark energy, and bounded by the speed of light. And that hierarchy fades into smoothness as scale increases. The largest structures are not infinite towers of matter. They are transient patterns in an expanding metric. Patterns we are fortunate enough to witness before cosmic acceleration hides them forever. There is one more layer to this that makes the idea of the most massive structure even more subtle, and it has to do with time. We keep talking about size and mass as if they are static properties, as if the universe is a frozen map and we are just pointing at the biggest region. But structure in the universe is not fixed, it evolves. What counts as the largest structure depends on when you look. In the first few 100,000 years after the Big Bang, there were no galaxies, no clusters, no filaments. The largest structures were simply tiny density fluctuations imprinted in the hot plasma. The universe was almost perfectly smooth. The amplitude of fluctuations was on the order of 1 part in 100,000. At that time, the largest structure was effectively the entire observable region itself because no nonlinear collapse had occurred yet. Everything was linear perturbation. Gravity had not yet carved out the web. Fast forward a few 100 million years. The first dark matter halos collapse. Small protogalaxies form. The largest structures are modest compared to today, perhaps a few million light years across. The web is faint, embryonic. Fast forward several billion years. Galaxy clusters assemble. Filaments thicken. Walls become prominent. Gravity has had time to amplify initial differences. The universe becomes dramatically structured. Right now, we live near the peak of large-scale structure visibility. Clusters are massive, filaments are extended. Superclusters and walls are identifiable across billions of light years. The contrast between voids and overdense regions is strong, but this will not continue indefinitely. Dark energy is accelerating the expansion of the universe. That acceleration suppresses the growth of structure on large scales. Over time, fewer and fewer new massive clusters will form. Existing clusters will merge locally, but supercluster scale collapse will not occur. In the distant future, tens of billions of years from now, clusters will remain gravitationally bound internally, but they will drift apart from one another. The cosmic web will effectively fragment. The large-scale connections between clusters will stretch beyond causal contact. Eventually, every gravitationally bound region will become an island universe. Observers inside such an island will see only their local cluster. They will not detect distant filaments or walls. The cosmic microwave background will be redshifted to wavelengths so long that it becomes undetectable. Evidence of large-scale structure will vanish. From their perspective, the largest structure in existence will be their local cluster, which means that largest structure is epoch-dependent. Right now, the largest identifiable overdensities span billions of light years. In the far future, the largest structure accessible to observation will be a single merged cluster, perhaps a few million light years across. The universe is not static in its architecture. It grows complexity. Then it erases it. Gravity amplifies structure. Dark energy dilutes it. And this tension determines the maximum scale of meaningful organization at any given time. So when we talk about the most massive structure in the universe, we are really talking about the largest structure that has had time to form before expansion limits further growth. This is not just a statement about mass, it is a statement about cosmic timing. We live at a moment when structure is both large and still visible across enormous distances. Earlier in cosmic history, it was smaller. Later in cosmic history, it will be isolated and diminished in visibility. The largest structures are therefore not permanent monuments. They are transient configurations in a universe evolving under competing forces. And that may be the most important realization of all. The most massive structure in the universe is not defined solely by how much matter it contains. It is defined by how far gravity was allowed to sculpt matter before the expansion of space began pulling the sculpture apart. If we strip away the drama and focus only on physics, the search for the most massive structure reduces to a balance between two equations. One equation describes gravity pulling matter inward. The other describes the expansion of space pushing matter apart. Every structure in the universe exists somewhere along the spectrum defined by that balance. At small scales, gravity dominates completely. A star is bound, a galaxy is bound, a cluster is bound. The escape velocity exceeds the expansion velocity at those scales. At intermediate scales, gravity partially dominates. Superclusters show coherent flows of galaxies toward dense regions, but they are not fully bound systems. They are in transition, regions where gravity once had more influence than it does now. At the largest scales, expansion wins. Matter cannot collapse into ever larger superobjects because the background metric of space is accelerating outward. The growth of structure effectively freezes. This introduces a physical ceiling on how large a bound structure can become in our universe. Cosmologists calculate this using the concept of the maximum turnaround radius, the largest radius within which matter can remain gravitationally bound against dark energy-driven expansion. For a given mass, there is a corresponding maximum radius at which gravity can overcome expansion. Beyond that radius, expansion dominates and prevents collapse. For the largest galaxy clusters, this radius is on the order of tens of millions of light years. This means that even if there are filaments stretching for billions of light years, they cannot behave as single gravitational objects. They are too large for gravity to bind coherently under current cosmic conditions. So the largest gravitationally meaningful structures are limited by cosmological parameters. If dark energy were weaker, larger bound systems could form. If matter density were higher, gravitational collapse would be stronger and more extended. If dark energy were stronger, even clusters might not remain stable. The scale of the largest structures is not arbitrary. It is encoded in the fundamental constants and energy content of the universe, and that leads to something deeper. The size of the largest structures is a reflection of the universe's composition, roughly 30% matter, roughly 70% dark energy. That ratio determines the era we are in. In a purely matter-dominated universe, structure would continue growing indefinitely. Larger and larger bound systems could form. In a dark energy-dominated universe like ours, structure growth halts at large scales. This means we are living near the upper limit of possible large-scale organization. The cosmic web as we see it today is close to the maximum complexity allowed by our cosmological parameters. Clusters may merge locally, filaments may thin, But no new gigantic gravitational super-entities spanning billions of light years will ever collapse into singular bound systems. The universe has a structural ceiling, and that ceiling is determined by the accelerating expansion of space itself. So when we ask what the most massive structure in the universe is, we must accept that the answer is constrained by cosmology. There is no infinite ladder of ever larger bound objects. There is a maximum scale of gravitational cohesion. Beyond that scale, matter is organized statistically, not dynamically. The most massive bound systems are galaxy clusters. The largest coherent overdensities are cosmic walls and filaments. And the total matter distribution across the observable universe represents the largest pattern of structure we can measure. But none of these are eternal. They are snapshots in a universe whose expansion rate dictates how large structure can become. In other words, the largest structure in the universe is not just a question of mass. It is a question of cosmological balance, gravity versus expansion, matter versus dark energy. And we exist precisely at the moment when that balance still allows us to see the web in its full extent. There is another way to approach the idea of the most massive structure, and it forces us to rethink what we mean by mass itself. Up to now, we've been counting stars, galaxies, dark matter halos, integrating solar masses across cosmic volumes. But mass in cosmology is not just about matter. It is about energy density shaping space-time. In general relativity, mass and energy are interchangeable. Energy density curves space. Dark matter curves space. Ordinary matter curves space. Even radiation and dark energy contribute to the curvature of the universe. So when we talk about the largest structure, we are really talking about regions where the curvature of space-time deviates from the cosmic average. Galaxy clusters create deep gravitational wells. Their space-time curvature is measurable through gravitational lensing. Filaments create extended, shallower curvature patterns. Voids create underdensities, regions where curvature is slightly less than average. But on the largest scales, curvature approaches uniformity. The universe, averaged over sufficiently large volumes, behaves like a smooth, expanding manifold described by the Friedmann equations. Local deviations exist, but globally the geometry is simple. This means that even the largest walls do not significantly alter the global curvature of the universe. They are perturbations superimposed on a nearly uniform background metric. That is important, because if a structure were massive enough to dominate curvature on cosmic scales, it would distort the universe globally. We would observe large anisotropies, directional expansion differences, strong deviations from isotropy. We do not. The cosmic microwave background is isotropic to 1 part in 100,000. That tells us that no single structure dominates the universe's global geometry. So the largest structures, while enormous by human standards, are small perturbations relative to the total cosmic energy content. This is counterintuitive. A wall billions of light years long sounds dominant, but relative to the observable universe, it is a fluctuation, a peak in a gently rolling density field. When cosmologists calculate the variance of density across increasing scales, they find that variance decreases with scale. This is called scale-dependent clustering. The universe becomes smoother the larger the volume you examine. There is no runaway hierarchy where ever larger structures dominate. Instead, there is a smoothing trend. This tells us that the universe has a characteristic scale of structure formation set by initial conditions and cosmological parameters, beyond which contrast fades. And that scale is not infinite, it is finite. The cosmic web is dramatic because we observe it at intermediate scales, where contrast is still visible but not overwhelming. If you zoom in too far, you see galaxies and clusters. If you zoom out too far, you see uniformity. The most massive structures exist in between. They are not the final level, they are the midpoint of cosmic organization. And here is something even more striking. If we lived in a universe with slightly different parameters, a bit more dark matter, a bit less dark energy, the largest bound structures could be larger. If dark energy were zero, gravity would continue to assemble matter into increasingly large systems over time. Eventually, superclusters could collapse into truly gigantic bound entities. But that is not our universe. In our universe, dark energy ensures that the growth of structure slows and asymptotically approaches a limit. So the largest structures we see today are close to the maximum scale allowed by our cosmological model. They are not infinite ladders, they are capped. And that cap is written into the energy density of the vacuum itself. So when we ask what the most massive structure in the universe is, the answer is constrained by the laws governing expansion. We can identify massive clusters, we can map colossal walls, we can describe the cosmic web, but we cannot point to a structure that dominates everything else gravitationally. The universe does not permit a single superentity that overwhelms its geometry. Instead, it permits structure up to a limit. Beyond that, smoothness returns. And that smoothness is not emptiness. It is balance. A universe expanding under the influence of dark energy, containing fluctuations carved by gravity, but never allowing those fluctuations to grow without bound. The largest structures are therefore expressions of constraint. They exist because the universe allows them. They stop growing because the universe limits them. And we live at the precise epoch when those structures are still visible in their near maximum form. When we zoom out to the absolute limit of what we can meaningfully describe, we reach something that is less about a structure and more about a boundary condition of reality itself. The observable universe as a gravitationally evolving patch inside a possibly much larger whole. The observable universe contains every galaxy we can detect, every filament we can map, every cluster whose light has had time to reach us. Its radius is about 46.5 billion light-years, not because that is how far matter has traveled, but because space itself has expanded while light was in transit. That sphere contains on the order of 10 to the power of 25 solar masses of matter, when dark matter is included. That is an unimaginable total. If you attempted to compress that amount of matter into a single bound system, it would exceed any structure we can conceive. But it is not compressed. It is distributed across expanding space. Inside that sphere, structure is hierarchical. Galaxies sit inside halos. Halos sit inside clusters. Clusters sit at nodes of filaments. Filaments outline voids. And all of this exists within a metric that is stretching. The observable universe is not bound as a whole. Galaxies near the edge of our observable horizon recede at effective velocities greater than the speed of light due to expansion. They are not gravitationally tied to us. They are moving away as part of the global expansion of space. If we imagine freezing expansion, gravity might eventually pull matter together on larger scales. But in our universe, expansion continues and accelerates. That means the observable universe will not collapse into a single megacluster. It will fragment. Over immense spans of time, only gravitationally bound regions will survive intact. The local group will merge into a single elliptical galaxy. Nearby clusters will drift beyond our horizon. The cosmic web, once visible, will fade from view. So the observable universe is both the largest mass-containing region we can define and a transient snapshot. But there is an even deeper layer to this discussion. Cosmology allows for the possibility that the universe beyond our observable region extends vastly further, perhaps infinitely. If space is flat and infinite, then the cosmic web likely continues beyond our horizon. There may be walls larger than those we have detected. There may be overdensities spanning scales beyond our current survey limits. But because light from those regions has not yet reached us, they are not part of our observable structure. This creates a profound limitation. The largest structure we can meaningfully discuss is limited by causality. We cannot empirically measure beyond the cosmic light horizon. So the largest structure in the universe is, in practice, the largest structure within the observable universe. Beyond that, statements become speculative, and within the observable universe, structure does not scale indefinitely. It plateaus. Matter fluctuations average out beyond certain scales. The power spectrum of density perturbations flattens at long wavelengths. That flattening reflects the fact that inflation produced nearly scale-invariant fluctuations, but with finite amplitude. There is no evidence for a single density perturbation spanning the entire observable cosmos with overwhelming dominance. Instead, there are many large fluctuations, some extreme, some modest, all embedded in an almost uniform background. So if we ask for a single, definitive, most massive structure, the honest answer may be this: there is no singular cosmic titan towering above all others. There is a network, a distribution, a statistical pattern of overdensities shaped by gravity and constrained by expansion. The most massive bound objects are galaxy clusters. The largest coherent overdense patterns are immense walls and filaments. The largest mass-containing causal region is the observable universe. Beyond that, there may be more universe repeating similar structure on scales we cannot observe. But within what we can measure, structure reaches a maximum scale and then smooths into near homogeneity. The universe does not build infinite hierarchies of ever larger objects. It builds complexity up to a limit set by its own expansion history. And that limit defines the largest meaningful structure we can identify. Everything beyond that is either smooth background or forever beyond our horizon. If we gather everything together, the stars, the galaxies, the clusters, the filaments, the walls, the observable universe itself, the question that seemed simple at the beginning dissolves into something far deeper. There is no single, ultimate cosmic monument. There is no final object at the top of a hierarchy. Instead, there is a layered architecture governed by scale-dependent physics. On small scales, gravity dominates completely. Stars form. Galaxies rotate. Clusters bind thousands of galaxies into gravitational wells, weighing quadrillions of solar masses. These are true objects, dynamically coherent, self-contained, resisting the expansion of space. On intermediate scales, gravity and expansion compete. Superclusters form vast flow basins. Filaments stretch across hundreds of millions of light years. Walls align galaxies into colossal arcs and sheets. These contain enormous cumulative mass, but they are not singular gravitational bodies. They are patterns of enhanced density, not unified structures. On the largest scales, expansion wins. Dark energy stretches space faster than gravity can assemble matter. Density fluctuations smooth out. The universe approaches statistical homogeneity. Structure fades into near uniformity. And yet, within the observable universe, the 93 billion light-year sphere defined by the speed of light and cosmic history, the total matter content is staggering. Dark matter heloscaffold galaxies. Hot gas glows in X-rays inside clusters. Voids expand between filaments. The cosmic web stretches in every direction we can measure. This web is not decorative. It is the amplified imprint of quantum fluctuations born in the first fractions of a second after the Big Bang. Microscopic energy variation stretched by inflation became density differences. Density differences became gravitational wells. Gravitational wells became galaxies. Galaxies became clusters. Clusters aligned into filaments. Filaments formed walls. Walls traced the cosmic web. And the web exists only because gravity had time to sculpt matter before dark energy began accelerating expansion. The most massive bound structures are galaxy clusters, the largest true gravitational islands in the universe. The largest coherent overdensities are immense walls spanning billions of light years. The largest mass-containing region we can define is the observable universe itself. Beyond that, there may be more structure, perhaps infinitely more, but it lies beyond causal contact. And even this grand architecture is temporary. In the far future, clusters will remain bound internally, but drift beyond each other's horizons. Filaments will thin. The cosmic web will fragment. Observers in that era will see only their local gravitational island. The largest visible structure will shrink dramatically. We live in a rare epoch, one where structure is both vast and still observable across cosmic distances. The universe does not culminate in a final megastructure. It produces a maximum scale of organization determined by its initial conditions, matter density, and dark energy content. Then it stops, then it stretches, then it smooths. So the answer to the question is not a single name, it is a realization. The most massive structure in the universe is not a solitary object. It is the large-scale distribution of matter shaped by gravity across billions of light years, the cosmic web, bounded by the observable horizon and constrained by expansion, a structure born from quantum noise, amplified for 13.8 billion years, and slowly being pulled apart. And we exist inside one of its smallest threads.